Okay, good afternoon. My name is Dennis Hancock. I get to be the Center Director at the U.S. Dairy Forage Research Center, just down the road here in Madison is our primary base. We also have a research farm in Prairie du Sac and a location up in Marshfield, more in central Wisconsin there. We have a little bit of an unusual situation today because this afternoon our speaker had a bit of a COVID concern, and so instead of showing up, he passed along a video that we will be playing. But we've got a little bit of a bonus to go along with that. Um, as it happens, we have our friends at Dairyland Labs have actually been doing some work alongside um, uh, with Matt Digman and looking at some of these handheld NIRS devices. And at the end of today's presentation, we have Kyle Taysom, who's from the Dairyland Lab. He's going to share some of his experiences with it, kind of complement some of what Matt's been going to talk about in the video, and then hopefully answer any questions that you might have about the presentation today. So we're going to start with that video. I do apologize for the fact that we're having to do this by video, but I think in the interest of everyone's safety, I think it's a good strategy here. So let's get going here. I'm going to, hopefully the sound is still working well.
Good afternoon, and thank you for attending this talk. I would like to talk today about how handheld NIRS instruments measure up. My name is Matthew Digman. I'm an assistant professor and agricultural engineer at the University of Wisconsin, and my co-authors are Jerry and Debbie Cherney at Cornell University. So it's common now in these types of presentations to present the end at the beginning, and hopefully over the next 20 to 30 minutes I can build the case that handheld NIRS instruments have their place in forage analysis, but it's important to remember the context of that place. And what we've found so far is that the sample preparation has more to do with the utility of these devices to predict forage quality than the devices themselves. So the analogy that I would like to present here is that we have different instruments that we use in my field, engineering, to measure things. In the lower right, we have a tape measure, and we use this for measuring, and this particular one probably for measuring large distances, possibly for surveying or laying out a large building. Then we have our caliper, which we use for finer measurement. And then finally we have the micrometer, which we use for very precise measurement, machining parts. The tape measure in this analogy really is using a handheld device in an as-fed forage. In as-fed forages, we have a lot of moisture, we have a large particle size, we have a lot of heterogeneity in the material itself, and we would expect to get all of those things to weigh in on our precision of our measurement and our accuracy. The next group of measurements would be more consistent with the caliper, would be using a handheld device in dried and ground samples. Here are the samples. We've gotten rid of the influence of moisture. We've ground the sample to homogenize it and get rid of that heterogeneity, and we can get a lot better prediction. And here we could expect to predict forage quality traits as well as that initial forage moisture content that we probably are predicting in the field. And then finally, with wet chemistry, this is where we really can improve our standard error. We can get a very precise and accurate measurement, and this is really why wet chemistry remains to be the gold standard. So to build up to that endpoint, I would like to first give you just a very brief background on NIRS instruments. I would like to give you a case study of using handheld devices for predicting forage quality in dried and ground forages. And while this might not be practical for our on-farm use, because most farms don't have the time or facilities to draw and grind samples, it does give us an indication of how these instruments compare or how these instruments measure up to instruments that are commonly used in forage quality prediction at the laboratory. Then finally, a very recent publication by our team has looked at the in-field performance of a couple of handheld NIRS devices. Finally, I would like to just give you some of my thoughts of how you might consider how these devices might work for you on your farm. So the background, and this is the abridged version of the background for NIRS, but I think it's important to start here. Just think about what we are doing. We are looking at light, electromagnetic energy in the near infrared. So in the IR bands of light, we know we can use those types of light sources to heat things, right? We know especially organic molecules absorb quite a bit of IR light. And you will be able to witness this at your local Quick Trip when you're looking at the heat lamps above your lunch or your hot dogs, although most of those are on the heated rollers. But you know, you've certainly encountered using infrared light to keep food warm. And food and forages, both organic substances, absorb energy highly in that area. Well, there is such thing as infrared spectroscopy, but near-infrared spectroscopy gives us some absorption of the light, but not near total absorption. In this area of the spectrum, we're getting some light absorbed and some light reflected back. And this is really important in measurement. We don't want all of our signal to be absorbed by the sample. We want some of it to return to our device, which we are taking the measurement. And that's where near-infrared spectroscopy really has its advantages. And further, the types of molecules that are abundant in the organic material can be gleaned from this light that is not absorbed, this reflected light. And that's a big assumption that we use in this technique, is we assume that the light that wasn't reflected back into the instrument was absorbed by various molecules within the sample, which allows us to then develop a sort of chemical fingerprint. And that's what's really happening here. You see a handheld NIRS device here. You can see that light being reflected off of the forages. And if you can, it's probably a little bit fuzzy on the screen here today, but you can see a resulting spectrum. So the spectrum is really just this light that is reflected across each wavelength of light. So if we go back to our original image here, we can see that at 400 nanometers wavelength, we're in a visible area of the spectrum. And as we go higher past 700 nanometers, we get closer and closer to infrared. Well, a very common way to linearize the output of these devices is to take the log of 1 over the reflectance. And what this does is it gives us something called absorbance. So the spectrum that you see here and plotted in blue is actually the light that was absorbed. So we've already taken the light that was reflected, we took 1 over that, and then we linearized that by taking the log. And what we can see here from this graph that was produced by John Schenk is that there are certain areas within the spectrum that we would expect different absorption patterns based on the chemical bonds within the sample. And of interest are things that are bonded to hydrogen, will vibrate well in this area, and hydrogen linked to carbon, nitrogen, and oxygen. So one can see how this technique could be used to measure things like water and things like carbohydrates. You'll see we'll predict things that don't use these types of bonds, but might influence molecules with these types of bonds too. And there's quite a bit of efficacy of this technique for measuring things that are even inorganic. Well, there's a plethora of instruments out there that can be used to capture these spectrum And on the left-hand side, and I found this picture on the web and I really enjoy that this computer here seems to date the instrument. This gives us an idea of how long these instruments have been around. So this is a NIRS Systems, probably 5,000 instrument, which is still a workhorse in the forage industry today. And these instruments date back to the late 1990s and are only recently being discontinued by the company that now owns NIRS Systems, Foss. But the technology is tried and true, and you'll see from the data that we still use them as a benchmark for collection of these data, these spectrum. The next group of instruments came around heavy in the early 2000s. About 2007, John Deere and Zeiss came out with the first commercial on-harvester application of NIRS using something called the Harvest Lab, and there's several newer iterations than the one pictured here. And then we have handheld devices that have been developed in the time since then. And there are even benchtop devices that have sought to replace the venerable NIRS Systems 5000 and 6500 out there as well that use the diode array. And then more recently, I would say in the last 5 years, we've seen instruments based on MEMS technology, and these are micro electromechanical systems. And what these devices, and the exciting part about these devices, is we've really been able to miniaturize the spectrometer even onto a single chip itself by using advanced manufacturing techniques that are used for making MEMS devices like you would find in your GPS and other types of technology like that. And they actually, there's quite a bit of information out there on the web. And the question that we have as researchers as well, what are the limitations of these MEMS devices? Do they perform as well as the diode array and the filter-based instruments of the past? And I would say that I've now been around long enough to see one of these transitions. When I was a grad student, we were making this diode array transition, and there were a lot of concerns about that type of instrument and how it would compare to the filter-based instruments and the limitations of the technology. And I would say that I'm hearing the same kind of concerns being expressed now about the new MEMS technology. The next thing we need to think about, regardless of the construction of the instrument, is the type of detector that it uses. And you might say this is getting a little deep for a practical presentation, but it is important to know that there are two real main types of detectors out there, and they really changed the utility of the instrument to capture spectrum in the NIRS range. And the silicon, there are two types, the silicon-based and the in-gas-based, and the in-gas stands for the types of materials that are used to create the semiconductor. And so a silicon-based semiconductor is the same kind of semiconductor, the same kind of light detecting electronics that are used in visible light cameras. So you can imagine your smartphone and lots of devices out there. They're really low cost, but their efficiency to capture light, to detect light, is limited into the visible spectrum and just barely into the NIR. These more advanced, more costly to make semiconductors using the doping of indium, gallium, and arsenide, those detectors are much more expensive, but as you can see, are a lot better at gathering light in the NIRS region. And if we can gather more light in the NIRS region, then we can get better spectrum and better predictions. So here is a nice comparison between some of these instruments that was published just last year by a group, I believe out of North Carolina. I can't remember now. I'm sorry. I don't mean to. The credit, the authorship credit is listed here. I'm sorry, I don't remember where the group was exactly from, but it was published in Crop Science. And here they compare again, our log 1 over reflectance or absorbance spectrum for the FOSS instrument. So that's the kind of tried and true instrument that's in orange here in the middle. And two low-cost devices. One is an NIRS instrument based on digital light processing, which is a MEMS device, and the other is an NIRS device called the microphaser, again, another compact device. But you can see here what we were just talking about, the wavelength range that is more limited in the smaller instruments, and that has a lot to do with the instrument design and the detector itself. But we can also see the differences in instrument response. So how much light were we able to get back in the instrument? And in fact, I would expect that the smaller miniaturized instruments would have a harder time imaging the sample, but in this case you see that the microphaser actually had more light that was captured by the instrument than the FOSS instrument. I would expect the FOSS instrument to be the benchmark here. The other instrument design consideration is how the instruments are handling variability throughout the day. And so these diodes, these light detecting diodes, are subject to temperature variation. So we can get something, I think I have a slide on it coming up here next. We can get something called dark current, where the diodes are actually also used for temperature measurement. So if you've heard of something called like an RTD, we actually look at the electronic signal developed by temperature variation in these diodes to measure temperature. So they can measure both temperature and light. Now, to compensate for that, instruments include something called referencing. And so you can imagine as your temperature varies, you may be generating more current in the diode based on temperature over time, so if the temperature rises or lowers, and that could influence what you think, what you are perceiving as light rather than as light reflected from the sample. So let's say you measure a sample and it's cold outside, you'll get one reading, and if it's warmer, or if the sample itself also, temperature matters, but the instrument temperature we're talking about here, the instrument temperature changes, you'll get a change in that. So the way that instrument manufacturers compensate for that is something called referencing. And depending on how the instrument is designed, that the referencing might be built into the instrument, like is shown here at the Harvest Lab in this polyspec, or it might be an external reference that you apply to the instrument. And there are pros and cons to different ways of referencing the instrument, but it's important to think about working with an instrument that is utilizing this reference regularly to compensate for dark current, because all of these instruments have that problem. Some more expensive instruments in the laboratory and advanced instruments actually try to cool the diode array to maintain the temperature internally. I would say that most handheld NIRS devices don't do that as more of a cost consideration. And then the final part of the instrument to think about is the calibration. And this is where I think is the biggest differentiator in instruments is how is that spectrum related to your forage quality parameter that you're predicting? So how did they build the calibration for protein, for fiber, for moisture? And how is that calibration maintained over time? So have they built that calibration with data from your region, from your country? If they built the calibrations in Europe, did they bring some samples in from North America to update that calibration or to look at its efficacy here? Are they working with a lab here in the United States that would help them not only build localized calibrations but maintain them, because these calibrations are a living thing. They do change from year to year, and your forage testing lab has a fairly elaborate quality assurance process for the calibrations that they utilize on the samples that you send in. And so likewise, the farm or the person or consultant using these instruments should have a similar process to ensure that the predictions are both accurate and precise. So just to kind of summarize the instrument portion of this talk, each constituent needs a calibration. They have to be maintained year to year. The thing that you need to understand is this is very time consuming and expensive, and it's probably costs more to maintain the calibration than the instrument is worth itself. This is really the big differentiator in my opinion. Again, on the technology differentiators here, I'm a big advocate for calibration, and there are some really good partnerships out there that are working hard on this. And then I put 3 dots because I'd say way further down the list are things you should be concerned about. What kind of optics does the instrument have? How good is the instrument at gathering light? So we're talking about getting this, we say signal to noise ratio. We want to make sure that we're getting a lot of the reflected light back into the sensor and imaging that light so that we can get a good idea of what the chemical makeup is of that sample. So once you have a good light in the sensor, then you want to have a detector that has a good wavelength range. Applied research in this area has really found that resolution is less of a factor with the current commercially available instruments. Nobody's really cutting too many corners on that, and they all seem to perform quite well. We've even done work where we've artificially reduced the resolution of the samples of the spectrum and predicted samples, and that works quite well. And then how stable is the instrument between readings? Okay, so now that we have that background out of the way, that we understand how we're gathering light and what matters as far as calibration, let's talk about some of these case studies. And these case studies that I'm going to present would be influenced by the calibration that was available in both the case studies that we looked at. Calibrations were provided by the manufacturer as well as built by the researchers. So we'll see a little bit of both of that. So some of these data need to be taken into that context. If calibration was built on a small sample set, we may not be able to extrapolate that to your scenario. So the first case study, this is using handheld NIRS and dried and ground forages. Now, I would be the first to admit, that using these handheld devices on dried and ground forages on farm is not very practical. But it does give us a really good comparison between the handheld device and the benchtop device. So 2 recent studies have been published. Our team has a 3rd study in review right now. And here are some quotes, from the Acosta study. The predictive power of both the handheld devices was similar to the benchtop device. The Berzaghi study, the Aurora NIR, and the digital light processing sensor that they looked at may provide an alternate to expensive benchtop laboratory equipment. So here we're seeing, based on these studies, that these scientists concluded that the handheld devices do perform as well as the benchtop device on dried and ground samples. So that's really good news. If the device is performing well, then we can have certainty that taking this handheld device, or some level of certainty, I should say, that taking this handheld device out into the field would be as good as taking the laboratory device in a computer cart, right? So I think that's really great news for the future of this technology. So in this first study, they've compared several devices shown here. We have the tried and true NIRS systems device. We have the Aurora NIR, which is a diode array device. We have the SIO device, And then we have this digital light processing spectrometer. So we have kind of the two miniaturized spectrometer devices. We have a diode array, which is kind of that intermediate device, and then the tried and true. So they had a nice cross-section of instruments in this study. So we need to set some kind of performance classification here, and a lot of times this RPD statistic is utilized for that. Really, the RPD can be calculated just from the R squared when plotting the predicted versus actual sample results. But the RPD is nice. It gives you a little bit more resolution in that area, especially when the R squared gets closer to 1. So it's commonly used. Here, Phil Williams, a giant in the NIRS industry, provides a classification, a set of classifications for forages based on the RPD. And I think these classifications are as good as any, especially since Phil was the one who proposed this statistic in the first place. And thinking about the R squared and the RPD, what we're really looking at is, what is the performance of this instrument given the variation of the samples that are being presented to it? So we're putting the prediction error or the precision of this instrument in context of the standard deviation of it. And I could provide the equation here, but if you're really into that, you could just Google it. It's pretty straightforward. So based on these criteria, we'll go back to our first slide, and I would say that tape measure really puts you at an RPD of about 3 to 3.4. And our caliper, I would say, is 3.5 to 4. And then our micrometer would be an RPD greater than 4. And if we go back to the previous slide, we see the tape measure is kind of our quality control. Our caliper gets us into process control. And then above that, we're in this excellent, where we really can rely on these results almost as if they were laboratory results. So one thing that this study by Brzagi looked at was the impact of wavelength range on the RPD when predicting forage quality. And here we can see that all these data were collected with the FOSS instrument, so there's no instrument variability in the data listed here. But here what we can really see is that wavelength range between 1100 nanometers and 2500 nanometers works really well for predicting forage quality. Now you might notice here that over in the red here, the NDFD, all of them are red. And this, NDFD is a more difficult parameter to predict for sure. I wouldn't take this as we can't predict NDFD with NIRS. Just with these 461 alfalfa samples, we weren't able to get over the threshold that we set for the RPD. So I colored here all of the samples green if the RPD was greater than that 3.5, and yellow if they were between that 3 and 3.5, and red if they were below that. Sorry, I should have mentioned that at the beginning. Now, what happens if we compare benchtop instruments with handheld instruments? So this is the benchtop instrument with the wavelength range restricted to be the same as the first handheld instrument here, so from 950 to 1650 nanometers. And here we see that the RPD statistic would tell us that the instruments perform very similarly. We have even some cases where one does better than the other, so I would say that we're within kind of the noise of our experimental design here. And then we do see that the handheld device that had the more limited wavelength range, so one that probably utilizes a silicon detector, really did not perform well for predicting forage quality. And the conclusion that Brzagi had in this paper was that wavelength range is really not appropriate for forage quality. Now, that doesn't mean that those devices wouldn't be useful in forages. It means that their utility might be limited to predicting things like moisture, which in my opinion is probably one of the most important things that we can manage on the farm. So looking at another study, this is that other study that's out of the Acosta paper in crop science. Here we saw very similar results. We're seeing that the handheld and the benchtop devices moving similarly with one another. It's a smaller set of data, calibration set, or the 210 samples were split between calibration and validation. We see, we did really well in crude protein and in vitro true digestibility, but we didn't do as well in some of the fiber parameters, specifically the NDF parameter, and in the ADF we had a differentiator where we just passed the threshold between the two instruments. So there are some limitations to these studies, and the study that we are in the process of getting peer reviewed, I didn't feel comfortable presenting that today since it's in review, and the reviewers might find some things that we need to fix. So I'm pretty confident in our results. I would say that our results support these two papers. We did look at a different instrument than these two papers, another MEMS-based instrument. But there are limitations to both these papers and the one that we just submitted. The calibration sample space, so we go out and gathering hundreds of samples and running them through wet chemistry and comparing instruments is time consuming and very costly. These papers and our paper haven't considered calibration transfer, so we got this to work on one instrument, but how well does that translate to other instruments of the same manufacturer? We do know that there is an influence of instrument to instrument variability even on the instruments, even on the original FOSS instruments and on the diode array instruments for certain. I would expect these instruments to have that same type of calibration transfer issue. And can we use the same techniques to mitigate that? I would suspect we can, as we do on the other instruments. And then, of course, the glaring limitation of these studies and our study, so I'm grouping us in there, that we perform these on dried and ground samples. So how does this perform on undried and unground samples? So that's our next case study. What is the in-field performance of these handheld devices in undried and unground samples? And this is a more limited study to a few instruments, but it starts to give us a picture of the challenge that we're going to have with getting these devices to work well. And again, I like to be upfront with what I think the conclusions are. I think that we're going to be able to do it. We're just not there quite yet with the calibration models that are available. So here are the devices that this study looked at. This study was performed by our group. We looked at the Aurora NIR. We looked at the NIR4 and the SAO device, and we also looked at a conductive type device, the HST, just for moisture. So if you're wondering how these moisture probes, we kind of compared, those are kind of the state of technology right now for forage moisture. It's aside from the gravimetric methods of, the Coster tester or microwave or air fryer. We look at the RPD for moisture, which I would say that moisture should be the low-hanging fruit for these types of devices. That the absorbance, there should be 2 moisture absorbance bands in that 950 to 1650 nanometer range. We'd have one around 970 nanometers, and we'd have one around 1440, so we should be well represented. The SAO device would only capture one of those bands, so that could explain lack of efficacy there, but if you look at our chart here, the SAO device didn't do that poorly relative to the other devices, so all of them wouldn't meet our standard that we've set up for RPD. The RPDs were quite low for all of these instruments using the calibrations provided. The Aurora device had provided calibrations for forage quality as well. And we had a similar story for the forage quality predictions. None of them met our criteria for RPD. So of course there's some limitations to this work. We only had one handheld NIRS device that we could evaluate for constituent prediction. We didn't, in this paper, look at the raw spectrum and developing our own calibrations. We were mainly evaluating the instruments as they were provided from the manufacturer. There could be some potential to improve these results. There could be some bias correction. There could be, the instrument provider could collect some local samples and help localize the calibration and use those local samples and reference data to improve their calibration. They could work with a local lab to improve the calibrations. So, you know, we see that there is going to be a challenge, and I think the challenge is more related to sample preparation than the instruments themselves. So that's why at the beginning of this presentation I presented this slide. You know, I think handheld NIRS devices will work well in moisture and as-fed forages and have good potential for predicting forage quality. But we need to do more research on that before we're comfortable with utilizing these instruments for any type of quality control, TMR rebalancing process. In dried and ground samples, the handheld NIRS devices are as good as the benchtop devices. That we've seen that time after time in the literature. They seem to do quite well. And, you know, we would see that sending in a sample into the lab and getting an NIRS prediction, I would actually put that in between these two, because the quality control and the quality assurance processes at these laboratories is really impressive. When you talk to folks at Rock River Labs or Dairyland Labs about their quality control processes, you know, they have a lot of automation and time invested in making sure that the predictions that they give you for your forage samples are reliable. And I'm really grateful and impressed with the work that they're doing. And then, of course, you can always go back to wet chemistry if you've got the money. I would say us researchers are even struggling with that. I think if you have a lot of samples, it makes sense to send them to the lab and have them run them through their NRS models that they've maintained and controlled. And if you have any questions, you should run a small subset through wet chemistry. So is on-farm NRS right for you? So some things to think about when you are thinking about any type of, you know, quality assurance processes. You know, what is varying, you know, and what is the value of monitoring that variability? So if I know that it's varying, what can I do with it? Is it actionable? Am I able to turn these data into, you know, management interventions on my farm? And I think the obvious one there is moisture. Certainly moisture is something you can correct for, and rebalancing aeration. Certainly monitoring changes in forages on a farm is valuable. But I think moisture is still the low-hanging fruit here. The instruments will do well in moisture, even if some of them don't perform as we hoped right now. I have confidence based on my past work that these instruments are really good at predicting moisture. And then the thing is, the final thing is, and as we looked at these tape measures, hopefully, and thought about this RPD statistic, we always have to think about what is the precision of this measurement, the precision and accuracy of this measurement versus the variability that's on my farm. And again, we have a couple of outreach articles out there on moisture, and we think that the story is good there. But you know, as you look at things like protein and fiber and digestibility, those types of things, you know, you'll have to make that decision for yourself. You know, what can you do about it? What is the response? And is this instrument giving me good enough data to make that decision? You know, when you are working with a manufacturer of these instruments or a provider, You're going to want to know how that data is formatted and transferred. So how can I develop a workflow around this data? Again, calibrations are important. How are they made? How are they available? How are they maintained? What is their quality control process? Can you send a sample into a lab, and will they look at the data from that? And then other things you could think about are, I imagine consultants are getting more involved in this. Could you work with a consultant to get access to this technology? In the past, when I've given talks on this, I've had the criticism that these instruments are too expensive, especially considering the value of forages. I would disagree with that, but it certainly is farm scale dependent. But just like we leverage technology from folks who do custom field work, custom operating, we can leverage this technology exactly the same way. So hopefully folks who are maybe running a smaller operation can keep an open mind about that and work through a consultant or a sharing situation. And with that, I guess I left my question slides in, but I'm not there. But I appreciate your time and attendance of this talk. I'm providing my email address here, so if you have any questions that you would like to ask about this presentation, I'd be happy to correspond with you through email.
Okay, as I mentioned, we also have a little bit of a bonus here. Someone actually who's familiar with some of this work and may be able to present a few comments and experiences of his own, as well as maybe field a few questions that you might have. Let me bring up Kyle Taysom, who is with Dairyland Labs, and they have been party to some of this work as well. Kyle, do you want to share some of your comments, thoughts on the presentation we've just seen?
Sure. Is this microphone working all right? So like you said, I have quite a bit of experience in this area. 15 years ago, I was at the University of Italy with Paolo Berzaghi, who's mentioned a lot in this presentation, with a team that built what eventually became the Dynamica Generale instruments, the Polyspec, the Aurora. I'd say probably 50% of the instruments you've seen make it to market came out of that group. Also been on the team with John Deere and Harvest Lab over the last 10 years, and the team, of course, at Dairyland Labs doing all of our internal calibration work. Just had a few points from Matt's presentation that I'd re-emphasize, and maybe one that I'll add. First is the main limitation we're giving up on accuracy by doing these on-farm is we're not drying and grinding samples. In our labs, we have over $500,000 of equipment dedicated just to drying samples. We spend more than $1 million in labor every year just drying and grinding samples. If we didn't have to do that to achieve the accuracy needed for formulating diets, we wouldn't do it. So when we go to on-farm, we're just giving up that ability. As Matt said, the next limitation you run into on accuracy is going to be determined by the wavelength range on any of the instruments. There's been instruments that came to market with 2 wavelengths, 200 wavelengths, or 2,000. And that's going to set the upper limit on how accurate those instruments can be. After we deal with not drying and grinding, after we deal with the spectral range, then it's really up to the calibration team to develop models that can fulfill the potential of the instrument. Fortunately, we're at a nice turning point right now where we can do a lot of cloud computing. Most of the new devices are set up on some type of cloud-based support, which lets us iterate quickly, also opens up new levels of computing that are available, which opens up new mathematical applications we can use to maximize those instruments. The one point I'll add to Matt's here is if we don't use these to test more samples and change our behavior, there's no point in doing this. If we're just going to take the samples we send to the lab and run them with the handheld instead, all we're achieving is a more expensive, less accurate analysis, right? What these instruments allow us to do, though, is open up new decision-making opportunities. For example, if I'm at a feed mill today, maybe I'm doing some QA analysis I send to the lab, and pretty much the only decision I can make is build up multiple samples over time and make some formulation adjustments. But if I had a handheld NIR, now I'd have the ability to measure every incoming load and accept and reject those loads as they come into the mill, opening up a new decision point opportunity. Similar if I'm on a dairy farm, I'm probably measuring moisture frequently. If I have a handheld NIR, now in the background, while I'm measuring moisture, I can detect changes in my forage quality. So instead of guessing, well, I'm switching to a new crop, I need to send a sample to the lab, I'd actually detect every day what's going on with quality and know when the quality changes. So if we can use these instruments to test a lot more frequently and make new types of decisions, I think there's a role for them. If all we're doing is substituting work we're doing at the lab today, I think that's miscast, probably. I'd be available for any questions, clarifications people want to walk through.
Yeah, Kyle, I think that's a great summary, and I think the combination here of these presentation and your follow-up has been really good and informative. The management aspects, I think, really are the key, right, as to what is this actionable plan that you're going to put into place after getting this data. And, you know, the moisture being one of the more prominent ones, but we heard yesterday about the potential ability to predict leaf loss, and perhaps eventually there might be an opportunity to you know, in the field, be able to make tweaks to the machine, or maybe we delay a little time before we do baling to minimize leaf loss or something like that. Questions from the audience about the role these handhelds might play and maybe the future of them? Sure.
So if I understand the question, it was kind of around with the low RPD values presented in some of those studies, maybe where did the calibrations fall short, or what was the root cause of that? Yeah. So the question was specifically on that, I think the last slide about moisture RPDs and why they were low and where the calibrations came from. I'm not sure. I wasn't involved in that study. Based on what Matt said, my understanding is that those calibrations came directly from the suppliers, and they just ran them like any consumer buying them off the shelf. Could be wrong about that. I was a little surprised because all of the instruments should be able to do moisture. It's by far the easiest thing to do by NIR. Not sure really where that fell apart, but they're all the instruments are definitely capable of doing moisture. Whether the calibration teams build the models to let the instrument achieve that, you know, I guess is an open question.
Yeah, that would definitely be a good one to follow up with Dr. Digman on, and that may be something that'll be borne out in a paper in the future on that too. Other questions? Well, I appreciate especially Kyle coming up on kind of short notice. We had this issue developed this morning, so we recruited Kyle to come in and talk. Let's give Kyle at least a hand, and we'll relay that appreciation to Dr. Digman as well. Thank you all for joining us. We'll have one more seminar session tomorrow morning at 10 a.m. Look forward to having you back here if you're still able to be here. And thank you, and I hope you have a great rest of your day here at Expo.